Prostate cancer is the most common non-cutaneous cancer in North American men, affecting 1 in 8 men in their lifetime. There are several methods of screening, but the gold standard is the core needle biopsy. The biopsy is most often guided using a 2D endocavity ultrasound probe, like this one, with an attached biopsy gun. The probe is inserted in through the rectum, and a needle is fired to collect a tissue sample. This sample is sent for a histopathological analysis. Unfortunately, the current method has a high false negative rate, so patients are frequently asked to repeat the uncomfortable procedure. 3D guidance is needed to improve targeting accuracy and for rebiopsy patients to integrate the previous core locations. This is done using spatial tracking and the 2D image to target and record biopsy cores. Unfortunately, during the freehand biopsy procedure, the prostate moves and deforms, so spatial tracking of the probe is not enough. We need to use the 2D information from the image to maintain alignment with the biopsy plan. We present a 2D to 3D registration framework for use in freehand prostate biopsies. First, we generate a 3D ultrasound from a tracked axial sweep. This reference volume is used for target planning. Next, we perform the sliced volume registration consisting of 2 steps: a rigid registration to account for the bulk motion of the prostate, and a non-rigid component to account for deformations. Currently, we achieve a mean target registration error of around 3 mm for the combined method. For the rigid alignment step, we minimize the sum of squared distances between image intensities. This method alone is highly susceptible to local minima due to the limited spatial information and the low signal-to-noise ratio of ultrasound. So, we introduce a constraint. We know that the pre-procedure sweep traces the rectal wall. During the procedure, the live 2D slice is also somewhere on the rectal wall. Thus, we constrain the probe to this pre-procedure trajectory. This accounts for any large spatial offset, ensuring the rectal walls coincide. For residual motion and for deformations, we use a finite element-based technique. This allows us to incorporate material properties of the prostate and surrounding tissue, letting it deform physically. The finite element model is driven by image forces as we simultaneously minimize the total strain and the SSD metric. This is the algorithm in action. The 2D slice first slides along the trajectory of the 3D volume, finding the best match based on image intensities. The finite element method then takes over, moving and bending the volume to achieve a better fit. Here we see the 2D target slice and the initial guess within the volume based solely on spatial tracking. As you can see, the boundaries of the prostate appear quite different between the images. After rigid registration, the prostate boundaries are much more similar, and there is a calcification visible at the same location in both images. Following finite element correction, the calcification is brighter in the middle. The volume has also deformed to better match the boundary features. Both stages of the registration method play significant roles. The trajectory-based rigid registration helps avoid local minima, bringing us to a good starting point for the FEM-based registration to take over. Our method is shown to be robust, locating some of the finer details present in the slice. If you'd like to find out more about our work, please come and find us. We would be delighted to discuss the details of the method and to answer any of your questions. Thank you.